but not with a good resolution. Was only to test the numerics, and then I will show you some results. Okay, this is we can put the full screen, or I have to leave it like that.
Control L. No, Control.
Okay. Sorry, but I don't know the Windows. Okay, so this is the work we are doing together with, I'm doing together with Carnevale and now with Pirozzoli. And in this, I'm not talking too much about the singularity, because when we wrote the paper, the people, they said that you don't have to talk about finite time singularity. You have to talk about vorticity amplification. So, but then for me it was a finite time singularity. So, but now I'm talking about also the relation between power law and spectra. Sorry, to go on? I don't know. This is going back, for sure. Okay. Oh. F5. Yeah, and then to move. Okay. Yeah. So I am interested to the power law, and we know that in the Euler equation and the Navier-Stokes equation is the nonlinear term that they are giving these power laws. So in wave number are the triadic interaction, and these in let's say, should be the vertical structure there should be related to the kind of power law in the energy spectrum. So we know that when we have turbulence, that means we have that is a viscosity different from zero. We have this n that is let's say minus 5/3. And then there is the exponential decay range. Sorry, this is weird symbol. I think is okay. And this should be the exponential decay range that is related to the should be a constant.
That square means epsilon, the dissipation rate, doesn't it?
Yeah, epsilon. But what is the epsilon here?
What else could it be?
Is it exponential a minus k? I think when you have an exponential range in
the viscosity not equals zero.
Yeah.
Viscosity.
This is when there is a viscosity. This is ni different from zero. This is the kinematic viscosity different from zero. So, so up to now, the people, when they were looking at this data we saw yesterday, they were looking at what I think Javier Jimenez defined as worms. That are round tubes with where there is a strong vorticity. That to me is not the structure in the inertial range. So in order to understand the structure in the power law, we need we have to have another power law. And so this power law we can find with the Euler equation. And so we don't have any exponential range. We should not. We should have a perfect power law. And I believe that at the singularity or near the singularity should be the power law should be k minus 3. This is what I was reading, but I never found one evident in the previous paper, an evident k minus 3 range. So my aim is to do simulation with two different initial conditions, the lambda-Hybel Taylor-Green, and also we are using now the Kidapels, to understand the structure in this power law, and then to see if there is any relation between this structure in in a power law, and the structure that we are going to have in a turbulent flow. So we are going to do the comparison between viscous and the Inviscid, and we are going to analyze the structure, and then we are going to see if there is some self-similarity of this structure. So about the numerical tools, up to now everybody doesn't trust any simulation with the second order finite difference, but finally I think I was able, after many years of fighting, to convince the people that this is not a very bad tool. And the important thing is that the numerics, this second order finite difference, should conserve the energy. The mass is clear. And so is the accuracy, and then now I found this also in other paper, that the accuracy is not important. What is important is to resolve the important structures. And so, and then to see that the comparison between the accuracy, the second order pseudospectral, and high order accuracy, this is what recently we did with Duponchel, that is a student of Wilkemans in Belgium, and we published just this JCP paper, Journal of Computational Physics paper, where we are doing this comparison. So we are taking the Taylor green, we are going forward up to t equal 10, and so we start from the very good vortex to completely, we have some k to the 2, and then we are going back, and we get the same initial condition. And then there is some comparison. I show only these, these results. And so this is E minus E0 divided by E0, and then you see the comparison, and then you will see, this is my point of view, is that you have the best results is for the second order finite difference. It's not, I was doing only the second order finite difference. The other simulations were done by the group in Belgium. So this is my conclusion. Somebody can have a different conclusion, but then this is what is coming out. The other thing is important is what he was saying, the timed bouncing. If you're using Adam Bashford, is worse than if you are using this low storage wrong cutoff that order that almost many people are using, and I got from Al Ray in Sapienza. And so this is about the, instead it's not my simulation, this is these people, I think, Graf et al., and then they were looking at these interacting dipoles, and also they were looking at different numerical methods, and also I think that this, usually what I'm using is this staggered grid formulation that is conserving, and so they did the analysis. It seems that this is a very good tool in order to study both the Euler and the Damier-Stokes equation without maybe going to the pseudospectrum. These are my results when you are doing the DNS, and I comparing the results of the finite difference that are, this is the forced isotropic turbulence, and then these are the finite difference. The other one is here because it's very resolved, compared with the results of Kida and Jimenez. And you will see that the comparison for in the range of K star is in Kolmogorov unit around 1, where there is the dissipation is rather good. So, and then they maybe what is nice of finite difference that they don't have this very large pile up due to their how you say, the pseudospectral when they are doing the aliasing.
Gibbs fringes.
No, it's the aliasing, I think, is giving this.
De-aliasing.
Yeah, they had to dealiase the code. No, I am not really an expert. I was always, So this is what they get. Sorry, I think you are using pseudospectral method. No, you have something like that always near at the.
If we increase the Kmax, the pile up.
Yeah, sure. This is okay, but then this is always so big. This pile up. This is with the finite difference, and then you have the. Okay, the comparison. This is the comparison to see in the compensated spectra for the k minus a third, and then you will see that the difference at the large scale are due to the this is forced, and so everybody is forcing up to k equal 3. That should be around here, and then there will be an effect on the inertial range. This is in Kolmogorov units. Okay, this is the comparison with Jimenez. So now let's go. This is our the forced turbulence, and now let's go to the Inviscid solution. So the question we are is there is a finite time singularity. It depends on the initial condition.
Yes, certainly. Yes, obviously.
What?
The answer is yes to your third question.
To the third or to?
To the third question, the answer is obviously yes. That's true.
Okay, so this is what I'm trying to the initial condition.
Yeah, take Rankine vortex or something.
Okay, so no, but then up to now the people were using what? He was using the Taylor green. Somebody was using Kida Peltz, and then he also was doing. You were doing Brachet. You were using both Kida and Taylor. So what instead, and then he was using this also orthogonal. You were doing, no, Bob? Orthogonal.
Yeah, I've done orthogonal.
Yeah. So what what we are using instead? Okay, this is let's say the proof. It should be. Let's say there should be. To have a solid proof with a numerical experiment, I think we need an infinite space and time resolution. We know that this is, we cannot have never, I think, maybe. And but then what we found in that paper, in our paper with George Carnevale, that from analyzing the data, we could derive one vorticity equation in the principal axis, the intermediate, the vorticity aligned with the intermediate, that is giving one equation similar to that. So that means that the S2, that is the intermediate strain, is proportional to omega 2. If you have that, there is a proportionality, and so you have one equation that is this, that we know, I think Kit told us this is there is analytical, it has a finite time singularity with t to the power minus 1. Okay? And so this is, so as initial condition, we are using the lambda dipole. Why we are using the lambda dipole? Because the lambda dipole is a self-preserving structure for the Euler equation. So it will not change while these two dipoles are approaching each other. So they will not shed any vorticity, they will not change the shape. I remember before Bob was showing us the simulation of the other one, sorry, that there was a negative vorticity. In this case, we don't shed any negative vorticity. The vorticity is always the same up to they start to interact with each other.
That is an advantage of using this.
Yeah. So they are interacting. I will show you the initial condition. This is what I'm doing. There are two dipoles, one like that, they are moving and then they hit, or we are using also 6 that they are moving slower, because this is, I was interested to have structure in all the box domain. Okay, so this is what is going to happen for the land, looking at the spectra. At t equal to 0, we have that the spectra is k minus 6. It stays k minus 6 up to t equal 1 while they approach. When they start to interact, the spectra is going to change the slope up to reach at the supposed finite time singularity, this k minus 3. And then here there are two simulations, one with the 512 cube, the other one is 1000 cube, that you'll see that up to a certain point they are very, they are good, is similar. So if we are going to have always increasing the resolution, we are going always to have the same spectrum, I hope. Cannot change. So this is the same spectra looking multiplied by K3, and then you will see that is reaching, to me, a satisfactory K3 averaging. I think there are two, but then this is what we got. This is the lamp dipole, the vorticity, while they don't do anything when they are, so they are very close, but still there is not the vorticity amplification. So this is the vorticity amplification. What this is, you see, is the vorticity amplification for 3 cases. LD1 is 2 lamp dipole, LT3 are 6, and then there is a KP is dipoles, and then you see Taylor Green, and then there is the Taylor Green. So what you see that when you have the dipole, if you are plotting omega max versus that, you would see that remain constant, and then to start to amplify. This is the inverse, and so should decay. So here there is both. Here is better because there are only 2 dipoles, they interacting before. When you have a 6, they moving slower because each one is slowing down the other one. But then you will see that also here you have something similar to that. I think there are oscillations. This simulation is 1000 cube. This is only 512 cube. And then you will see instead that the other 2 cases that there is at the beginning, there is this decreasing of the vorticity because of respect to the Taylor Green. And so to me, this is a very good feature of the lamp dipole. So there is no any decrease of vorticity then amplification, because this is the inverse. And so you see how the initial conditions are important. This is, for example, I am plotting close to the time of the supposed singularity, the omega, the variation of the entropy divided by omega 2, that should go as always Ts minus T minus Ts, maybe I did something wrong over there. No, but then this is the inverse, and so should go linear. And the TB is, I'm taking omega B, OB, and the other DOB and OB are these quantities at a certain time. So I'm scaling with this quantity at a certain time. And then I'm going to look at the last period when there is the strong vorticity amplification. And then you will see that this is the LD1 that is behaving quite well, should be linear, and then should go here if I have an infinite resolution, an infinite computer, and an infinite time of my life, but I'm old. And this is LD3, still is behaving quite well. And then I will see instead the key dipoles is going worse. This maybe is the reason why Kidapels nobody found that there was a finite time singularity. Huh? This is what. And then also the Taylor-Green. Here there are two simulations: the Taylor-Green with the 512, the Taylor-Green with the 384. So it seems that you were saying that is depending of the initial condition. Yes, you will see that maybe, I don't know if we found this more interesting initial condition in order to look at the finite time singularity. Okay, this is are the spectra, and then this is, you will see that we have this power law, always k minus 3, they are different, this is at the same simulation, I'm sure. And then here, clearly, this is the near the cutoff, and so, but then it's not important because this is multiplied by kq. So, but let's say these are the quantities that are the part of the spectrum where there is the entropy containing structure. I don't think this will be really important. But then I think all the cases, they give, except maybe the Kidapels, they give a satisfactory k minus 3. So perhaps this is some disagreement with the statement of Bob before. Okay, this is our the structure. This is our defined 1000 cube simulation. And then you will see that when these two vortices are interacting, this is our the structure. There are two vortex sheet like that with some curvature in this point. Then you will see. And now I am analyzing that. In that paper, this is what I was saying, that we analyze the data of the vorticity, omega 2 tilde is the omega 2 in the aligned with the principal, with the intermediate strain. We have this equation neglecting other term that maybe don't do anything. This equation is this is the one that has, for sure, a finite time singularity. Okay, this is to look at the vorticity amplification, and we check both the omega max and omega 2 max. The omega 2 is really taking almost all the vorticity magnitude. All the vorticity is in this omega 2. In fact, the previous, this, we are plotting here the omega max and the omega 2, you will see they are the same. The omega magnitude and the omega 2. And, okay, this is the entropy production, and that is going as T minus, Ts minus T3. Maybe there is always one error. Yeah, no, this is correct. And then is eating this supposed time singularity at 2.76. Now, this is I took from your paper, and this is what he found, and then I think he could not find. I was asking to him to give him his data. He said he doesn't have, so I had to take this data, from this data to plot, to compare, and then I will show you the comparison with him. This is instead how is evolving the Taylor-Green, starting from t equal to 0. This is at t equal to 0, and then is evolving. So this is the reason why there is always what we call the decrement here, because at the beginning it doesn't have a perfect power law. So there should be, this is the in time, so here there should be the k minus 3 plus the decrement that is maybe only a certain point is going to disappear. It's for sure when you reach the singularity. And this is our my data of the maximum vorticity versus with different resolution, and then for sure this is going to this if you increase the resolution. And okay, this is to see if we are reaching the k minus 3, and then to me, I'm reaching the k minus 3 with this. And okay, and then you will see that this k minus 3, this is between 4 when he stopped the simulation. I remember he was stopping the simulation at t equal 4, and then you will see that, and so you don't have a k minus 3 at t equal 4. So he was not able in his paper, I think, I don't know why you stop, but then there would be a reason why you stop.
Delta, the simulation we believe was not accurate enough at the resolution we were. So
Yeah, but then I think, look, this is what I got. If you're looking at this spectrum multiplied by K3, I think it's accurate, no? I can understand here, but this is really energy, small energy content. Okay. Yeah, okay.
just the spectrum is K minus n, and something that is decaying faster, that is an exponential.
Yeah, it's this.
Yes. And we stop the computation when we think we cannot measure anymore the exponential. That's why we stop.
Okay. So, but then, I was interested. So I think, but then you will see that at this point there is a really, in a very short time, is going to k minus 3. And this should be really something related to very important events that are coming in that range. Okay, so this is the spectra that I'm using. This is the entropy production that should go. At this point, yes, for the entropy production, that is still more important. There is that that difference. And okay, these are now the 3 fields I'm using in order to look at the structure. This is the Taylor Green. This is the lambda dipole. One lambda dipole. This is the isotropic turbulence. I want to see if there are similarity of the structure. This is the vertical structure in the lambda. I show this is a different view. So our sheet-like vortices like that. And this instead is the Taylor Green. And then you will see that there is one curve, the other longer, one short. But what I was interested so I want to analyze this structure. And so what I'm doing, I'm taking the spectrum, I'm filtering the field, and I'm taking out, I'm analyzing only a part of this. And from that, I have and then I put equal to 0 all the amplitude of the UK for outside this range, to look at the structures that are responsible to the part of the spectrum I would like to analyze. So this is what I have. This is the true vortex structure that I'm analyzing. This is one slide where there is the maximum vorticity. And this is the structure related to this part of the spectrum. So I'm taking out 0 of all these in wave number and then going back in the physical space to have this. This is the vorticity. So you will see that the shape remains, and then you will see that now in this, that is still k minus 3, you have that the structure is, to me, is self-similar. And then I will show you, this is still, there is some self-similarity here. Again, there can be one, it's not still quite resolved. And then here there is some contamination, but then I will show you this, that I'm rescaling the structure with the K maximum, and so you will see that around the maximum of the vorticity, this is in one plane, cutting, this is where there is the maximum vorticity, looking at the vorticity around this point. And then you will see scaled by the range of wave number that I am taking. And so you will see that they are they are self-similar in the lambda dipole. And this instead doing the same process for the Taylor-Green, and then you will see that still there is the same self-similarity, but let's say that, so we are going, in this case, okay, I'm taking this part, and so this is going to break everything, but then you will see that the self-similarity is less respect to the lambda dipole. This is in order to say that the initial condition can be important, and so I think the lambda dipole is a good animal to study these things. Okay, this is that is the PDF of vorticity. And then you will see how for the PDF of vorticity respect to, I think is the RMS. Here is a PD sigma. This is the turbulence that you see that you have a log normal distribution. Instead here you have the two cases that are completely different from the log normal. So this is a first evidence that the structure in this vortices are different from those in the turbulence. And then you will see here doing the filtering that the PDF of vorticity, this is scaled with respect to the omega. At each different omega, at each filtering, you will see that the shape of the distribution of the omega is similar. This is the omega magnitude, and so is self-similar also. This is the last part when we are close. And the same is occurring for the PDF. So from this, is let's say that let's say I'm trying to look at the structure when there is this power law k minus 3, and from this it seems that the structure are self-similar. Okay, and now let's say I want to understand why we have in forced isotropic turbulence we have this k minus phi third. Okay, we know that everybody doing any kind of simulation, forced simulation, we are forcing at a large scale, and has this k minus phi third. Again, here I'm plotting my results compared with the pseudo-spectral. And you will, and now I want to understand that. So instead to do the now I'm doing the Navier-Stokes simulation of this starting from smooth initial condition. So 6 dipole interacting, a different Reynolds number, and also for Taylor-Green and Kida-Peltz. So what we have? We know, let's say my personal view is that if with n with n equal to 0, we have a finite time singularity. And let's say that I was discussing with him, I would like to know which is a convincing proof. I am doing the simulation, I am doing numerical experiments, so I would like to know which is. Maybe the mathematician can help me because I'm not able to understand these things very well. So, but then when I'm having the Inviscid case, I'm stopping the simulation up to when I'm thinking that is well resolved, I have n minus 3. Instead, if I'm going to do viscous simulation, I have the minus 5/3. So clearly the equations are different. We have the viscosity. The viscosity is giving me this exponential range, and clearly the resolution is important. Now, what I'm trying to do, this is the comparison also from this is 512 cube simulation of the Inviscid case, and then I'm putting the viscosity. You will see that at a certain point this is not resolved. At a certain point, there is an effect of the viscosity on the behavior of the vorticity amplification. And this is the entropy, and here we have that is going to be affected when the Reynolds number is 10 to the 3, and then I will show now after. These are the spectra. You will see that this I was stopping this simulation mostly around this T when there is the supposed finite time singularity. And then you will see that there is some influence. But then, okay, this is again the spectra, the compensated spectra. And then this is the comparison of the vorticity, the entropy in time, to see this is if you put more vortices, you see that if you put 2 or 4 almost the same, because they interact before, because they have the speed is equal 1. When you have 3 of them, they slow down, and so they interact after. But then this is now the comparison. You will see that here are the two Inviscid cases. There is this vorticity amplification that is almost similar. I had to move these because they interact, but then you will see how they behave. And then this is the difference for LD3 at different Reynolds numbers. So to me, because here I should, this is only 5,000, in order to have, let's say, before was to go forward, I think you have to increase the resolution in order to have a very good simulation. But what is important is that at any Reynolds number, I have that at a certain point there is a maximum entropy. This is the inverse. There is a maximum entropy that then is decay. And so at this, this is what I'm, and so now, let's say we are going to look at the spectra. So in the first part, we see that all these cases, more or less, they give, this is k minus 3. We have a k minus 3, also with at any Reynolds number. Okay, at this, no, but then at the large scale, we have a k minus 3. And then this is when there is the entropy amplification. Then at a certain point, when you reach the maximum, we start to have the k minus 5/3. And we have the k minus 5/3. And then, okay, we are going to the effect of the viscosity. We are going to have the k minus 3/2. And then this is because we are at low Reynolds lambda. And we know that usually when Reynolds lambda is low, all the DNS, they give the minus 3/2. And okay, so what we have to look to understand the entropy, we have to look at the entropy equation. And so we have the most important term is the production, the entropy production, and then we have the dissipation. So this is how they behave. So at the beginning, the entropy production is 0 in all cases, and then it starts to grow. And then there is these three curves are the dissipation of entropy, and then you will see that the entropy production is much bigger than that. In that region between, let's say, in this part, we have when there is the vorticity amplification. Then there is the maximum. When there is the maximum, the two became equal, and then they remain, they balance during when the entropy is dissipated. And then here, if you are plotting, this is P, I think you were showing something like that, the entropy production versus the entropy, we have this 3 to the half, and not the one you were showing cube, no?
Yeah.
Instead, we have the 3 half, and then this is maintained.
This is Navier-Stokes, though.
Yeah, this is all.
Right.
Oh, Inviscid and Navier-Stokes. The symbols are Inviscid. I stop over there, and then you will see that they are k to the 3 half in this region. Then they remain k to the half always also coming back, because at a certain point the entropy is, the production is decreasing, and the entropy is decreasing, going forward. So why we have that? But it's very simple. If what I was telling you, when there is entropy, the entropy amplification, what I have, this is, let's say, the entropy, entropy production in the principal axis. Let's say that almost equal is almost this. This is the important part. S2, I said, is proportional to omega 2. So we have this that is quite simple. This is the reason why we have this omega to the 3 half. Okay, this is, if I'm going to look in time to this, and then you will see that the bigger one clearly is, we have, this is the omega 2 1 S1, that is very big, but then it's cancelling with the omega 3, because it's negative, big omega 2 is positive, S3 is negative, and so there is cancellation there almost equal, but so the leading term is the omega 2 S2, because S2 is very small. That means over there you have everything. And okay, so we have to look at this equation. This is the entropy equation and the straight. And so this is we know that there is some relation. So what I'm interested to look if I'm plotting out the joint PDF between this quantity and this quantity, and if they should be correlated with this S2, because this when this is 2, and then because I'm thinking if S2 is negative, it should be sheet-like structure. So what I'm trying to say that the sheet-like structure are responsible.
Are you showing us the entropy production at a single point or integrated over volume?
No, this is the joint PDF of all the points.
The thing before.
Before is the integral.
That was the integral.
Yeah, that is the integral of omega 2. So this is the total, okay? Now I'm going to show you how they are correlated with beta. Beta is the kind of structure. We know that if beta is negative, are sheet-like. If beta is positive, are the two. And so you will see that they are, but this is our 4 cases, I think. This is the Inviscid, then increasing the Reynolds number. No. Yeah, this is our when there is the vorticity amplification in the first part, and you will see that they are well correlated with S2, and the positive part, the quantity, this part is related to. I'm plotting the negative of that.
Alpha is the stretching rate, and beta,
yeah.
Beta is the middle eigenvalue of the rate of strain.
Yeah, it's this one.
Yeah. Okay.
So, but then there is the.
So beta is that one.
This one.
Oh.
Okay, so I think you were plotting this, but then you didn't do the PDF. You were doing only the joint PDF. You were doing the PDF of these quantities. Is correct?
Yes, that's correct.
Yeah.
Only the PDF.
You did, and so I'm doing the joint PDF, and so to see if there is some correlation. So it seems that they are quite correlated. This is I'm plotting the negative, and so in order to see that these quantities where there are the sheet-like structure. Okay, this is the switch. So this is when there is the maximum. Still, there is this correlation, and then again, also during the decay, but then in the first part, they are better behaving. Okay, now let's look at the structure, the last, for this viscous simulation. So we want to look at which are the structure, and so we are, let's say, doing the vortex adduction, and so we are using this lambda 2, I think, for the tubes, and then this is the method that the eigenvalues of this Oriuti recently. And so I'm looking at what is going on, looking at the you will see now the structure in only 1/4 of my simulation. So this is only one part. There are 6, but then there is a symmetry. So this is the tube, and so you will see, okay, this is our tube, this is our to be sheet-like structure, and then you will see that this is what is going to happen when we have this k minus, no, this is t equal to 0, when we have this k minus 6. Then we are going to have a k minus 3, and then you are seeing that these are the structure I was showing you. These are with this structure that are that are the most, to me, important. The other one are the tubes, and so, but the k minus 3 is related to that one. And this is what is going to happen when we have the k minus 5/3. And so in the k minus 5/3, you see that without doing the filtering, the structure, the tubes, the worms, they are coming out from any kind of simulation, not only forced. This is a very small range, k minus 5/3, but this is the structure not too different from the one we saw yesterday. Clearly, over there it was forcing, it was very long. This is only one-time realization, but this is the structure that are elongated sheet, but then, okay, so this is to summarize why is forming the k minus 5/3. And okay, this is I did another simulation starting from, let's say, if I'm doing a force, I stop a certain point, let's say at this time, and then I'm evolving this with the viscous, with changing the Reynolds number, increasing the Reynolds number. So this is the lambda are this one. This is instead are the two simulation. This is energy and entropy. This should be the entropy for the cases. And then what is interesting is to look, okay, the spectra, you will see both. They have also, this is the comparison, and so you will see that they have this the k minus 5/3 and then the exponential range. But what is interesting to look not to, this is the derivative is curious, but look at the flatness. The if you're starting from turbulence, you will see this is are the turbulence. Look, the flatness doesn't change too much, changing this is the flatness of the derivative. No, usually we plot that one, and you will see that they don't change too much. They go from 5, they increase depending on the Reynolds number. This is at the 3 derivative at 2 Reynolds number, but then they more or less they take again these values that is typical of turbulence. But also look instead at what is going to happen when these 6 dipoles are interacting. The flatness became huge, but then is reaching almost the same values of the so of the isotropic forced isotropic turbulence. So this is our the conclusion. So what we have, we think from our we are doing brute force, putting the equation maybe in a good with good numerics in the computer, and so we found that the Euler have a finite time singularity. The Navier-Stokes, they don't have a finite time singularity. And there is important the initial condition, especially for the Euler equation, and we think that the lambda dipole is quite good because it's shape preserving, also for this because we are interested interested to the spectra. I think what I should, but then to have interaction with a mathematician that maybe they can understand to withdraw some interesting things from this experiment, supposing that you believe it's a well done experiment, to get something that they can use to have what is a solid proof. And okay, clearly, if we want to have a more solid database, we have to go to have a more CPU, and but then somebody should give to us at least the computer to do this large simulation, and but here there are no sponsors, so thank you.
Okay. Well, we've time for a couple of questions. Yes.
Yes. So the initial condition of lambda dipole vorticity is concentrated in this antiparallel, right? And what about the stretching rate of vorticity? How does it look like?
So if you put a lambda dipole, let's say only one, 3D, without any disturbance, it's going to go like that always, and so there is no any stretching. I think I think I did that. I think, but doesn't do anything. Before I was doing 2D, but the important things I think they go like that. At the beginning, I was trying to see what is going to happen if I have vortice impinging like that. For any, but they don't do anything. They say they preserve the shape. It's very interesting. But that you can do in 2D. But I trust my code. My code, if I'm doing 3D on 3D simulation without any disturbance, it will stay 2D. Okay, so it will remain 2D. So if you take this vortex impinging with another vortex, you will see that this is during the interaction the shape is not preserving, but immediately after he likes to go again to the lambda. I think this is now there is a Gert. We have to look. Is a very good attractor. Any disturbance. We did this for 2D many years ago. That we were taking this vortex. We were putting instead to be circular, a perfect radius. We were putting like an ellipse. Immediately you want to go again to a circle, he is shedding the vorticity that he doesn't like. And this, many people are looking into the vorticity stream function should be linear around the vortex. So I think is a very good. Also, I think if you take any vortex at the end, you want to go to that. There were the people doing this. Montgomery was doing this simulation, 2D simulation. At the end, he found this a lambda dipole. if I remember, roughly.
Steve,
I'm sorry if I've misunderstood. It seems that for your land dipoles, you've got discontinuities in high derivatives.
Sure.
You know, isn't that asking for trouble if you're then trying to solve this numerically? Because you're going to have great difficulty keeping high accuracy.
Yeah, but then okay, but this is yeah. You remember the spectrum? The spectrum was k minus 6, no? And then I had. You remember I have this small pile up near the. Let's say this doesn't like. He doesn't like the vorticity discontinuous. But this is no. The vorticity is continuous. Is the vorticity derivative that is discontinuous. Okay. So let's say, okay, but this is going to go everywhere in the field, but then we don't care because it has very small vorticity. What I'm trying to, I believe that the vorticity amplification is where there is the vorticity. So these sheets that are forming are where there is a vorticity, are not forming where there is no vorticity. I don't think the amplification can be where there is this weak vorticity. I'm answering to your question?
I would support Paolo on what you just said, because the profile that I typically use is a Gaussian plus an exponential, and the Gaussian by itself is k to the minus 2. Which is far worse than what you're talking about, or k to the minus 4. It's worse than what you're talking about. I would recommend you add a hyperviscous smoothing to the very highest wave numbers, as I found was necessary.
I cannot.
Excuse me?
I can't.
Well, you effectively do it with numerical.
No, there is, sorry, in my numerical scheme, the energy is perfectly conserved.
No, I'm not saying use a hyperviscosity in your merits. I'm saying use a hyperviscous filter on your initial condition.
But it's going to...
Well, I found that these little bits and pieces can cause trouble.
Why not do it and show it makes no difference?
Exactly.
Sorry.
Do it and show it makes no difference, then we'll be happy.
Yeah, but then,
Smooth it a little
okay, but then I had to feel, okay, yeah, but then I had to do another simulation, and then to do a simulation, no, why? I can do with the
all my
512.
tests before doing my big monster calculation, just to see what the effectiveness on my laptop.
Yeah, okay, I can do this, but...
You do 64 cubed, 100
No,
cubed
64, no, but then now in your laptop you can do 256 cube in one afternoon, I think.
yeah, okay, look, it's 1 minute.
Sorry.
So let's thank our speaker, and we have to restart at 12:30 when Peter